Thanks again for joining us this morning for this next in the series of iGuide Virtual Consulting Offices, or VCOs. We are pleased to be able to offer these on a regular basis to allow scholars and practitioners to share information about their geospatial activities during an informal presentation focusing on these different technical topics. So today I'm super excited to introduce Dr. Geoff Boeing from the University of Southern California. And we're eager to hear about the work that he does with how to analyze different types of urban networks through spatial analysis. So Geoff, I'll turn it over to you.
Thanks, Diana. You all hear me okay?
Yes.
Great. Yeah, thanks for joining me this morning and what's probably your summer vacation right now. Um, so I'm going to talk a little bit about some of my work around urban networks and how our scientific understanding of them has evolved in recent years. And then what I'm going to do for the demonstration part at the end is walk you through the first bit of a tutorial for a Python package called OSMNX, which I developed and maintain. And I have a Jupyter notebook that I'll go through on Colab for that. But first, just kind of motivated. I have a talk for a few minutes here up front. So, um, as Diana mentioned, I'm an associate professor at USC in the Department of Urban Planning and Spatial Analysis. I'm also a faculty affiliate at USC Spatial Sciences Institute. I direct the Urban Data Lab here, and I'm also a non-resident senior fellow at the Brookings Institution in Washington. Now, most of my research revolves around trying to understand street networks. In particular, looking at user-generated data that offer us this sort of wealth of information about cities, human behavior, infrastructure. So pulling from things like GPS traces, transit card taps, volunteer geographic information, such as OpenStreetMap, which we have a screenshot of here, where we crowdsource information about the urban form and particularly transport features. So if you're not already familiar with OpenStreetMap, it's kind of like Wikipedia meets Google Maps. It's a worldwide mapping platform and geospatial database. It's collaborative. Anybody can contribute to it with some editorial oversight. And you can see in this screenshot of downtown Los Angeles that we have streets and transit lines, bus stops, metro stops, parks, hospitals, schools, building footprints, all kinds of amenities, points of interest, in addition to those networks. And what I use this kind of OpenStreetMap data for is to understand street network form. So by form, I mean some mix of geometry and topology. And most of my research investigates street network form in some way. And it's important for cities for several reasons, which I'll demonstrate here with this set of four street networks. Now, in this picture, we see four networks all held at the same scale of 1 square mile. Street networks and other urban transportation networks provide the sort of substrate and connective tissue that help to organize a city's human dynamics. When we hold them all at the same scale, like we do here, we can really easily see the pattern, texture, and grain of the street network and how it reflects different transportation paradigms, design technologies, politics, expressions of power, underlying terrain, local culture, economic conditions. For example, if you consider the, the histories and values embedded in the classic street grid, from Hippodamus's early urban design work in ancient Greece to the Law of the Indies and the New York Commissioner's Plan and the U.S. Homestead Act, the grid has been used for millennia to express a certain human order over the landscape, or to organize transportation around spaces of power and control, or to make land more amenable to real estate speculation and development. Alternatively, consider Haussmann's renovation of Paris in the 19th century and its planning goals, or the auto-centric form of U.S. Sunbelt cities and the notions of lifestyle and aspiration and privilege and exclusion that are very explicitly planned into certain types of cities and suburbs around the world. And in particular, all of these street networks demonstrate varying levels of connectedness, accessibility, compactness, resilience, and sustainability. And if we start to add in other urban features such as building footprints or land parcels, demographics, we can start to think about household accessibility to jobs, schools, stores, and other kinds of daily living needs. So here we can see how different the urban fabric looks in the top row in kind of 19th century urbanized North American cities, New York and San Francisco, versus informal settlements in the global South, in Monrovia and Port-au-Prince. Now, U.S. transportation planning in particular has restructured our country's urban network substantially over time. And as it's done so, it's redistributed access and equity for different groups. So here we can see kind of typical street network patterns from different eras. On the far left, we have the kind of classic deformed street grid from the early 20th century, basically what we saw throughout the 19th century up until the adoption of the automobile. In the center in the 1940s, this kind of early automobile-centric development, winding suburbs that still have fairly high connectivity, but were much more designed around driving gracefully through the neighborhood rather than being on foot. And then lastly, at the end of the 20th century, in the 1990s, you can see a really typical 90s development. A lot of cul-de-sacs, very few intersections, and when there are intersections, they're usually three-way intersections rather than four-way intersections, giving you as many choices for how to move through the urban fabric. So on the left, those kind of historic street grids traditionally provided the interconnectivity and density that planning researchers have identified as important factors for active travel, pedestrian safety, being able to efficiently provision a transit system, and reducing motorized vehicle travel. That's all just one factor. So land use, crime, and others matter too, in addition to street network design. But in the 20th century, grids started to decline in planning practice, as we see here, as urbanization sprawled around automobile dependence. And today we have this problem of planners around the world, and certainly in the US, working in car-dependent cities that are choked with car gridlock and facing these intertwined public health crises from physical activity and environmental pollution while we struggle to impede climate change. So physical design matters for several reasons. Denser and more connected street networks, like you see on the left here, are associated with higher walkability, lower vehicle kilometers traveled, and better pedestrian safety. And so, what I've tried to do in recent years is understand to what extent the physical design of our street networks matches with the sort of best practice in the research literature today. And one way I've done that in the US is looking at where those classic street grids still exist. When we talk about a grid, we're talking about a very orderly kind of spatial planning. And to visualize that idea of order, I use these polar histograms to measure the entropy of a street network. So here we can see Manhattan, New York, and its polar histogram. And the way you read this is that each bar of the histogram represents 10 degrees around the face of a compass. So north, south, east, and west. And the bar's lengths show the frequency of streets in that place that are pointing in that direction. So Manhattan's an easy one because you can see the island is offset about 29 degrees from true north, and its polar histogram reflects that. So we have a grid. There's four bins that contain most of the streets, and they're offset by about 29 degrees from true north. There's some noise around the histogram for some streets like Broadway that don't follow that, but it's swamped by how many streets are in that planned grid from the New York Commissioner's plan. Now, if we look at a place like Detroit, we see something a little different. So Detroit has two main grid plans. The first, older one, is aligned offset from true north along the river in central Detroit. And there's a newer grid, more aligned to true north, that kind of wraps around it in the rest of the city. And we can see both of those grids show up in its polar histogram. One offset from true north, and then a larger one, north, south, east, and west. Fairly low entropy. And if we look at other places, we start to see that not everything is quite as orderly as places like New York and Detroit. For example, Boston has a higher entropy, a lower ordered street network, for a variety of historical reasons. So Boston is an amalgamation of many smaller towns and villages over the course of more than 400 years. Um, it has some grids, such as in South Boston and in the Back Bay, but they don't align with each other. And the rest of the city doesn't really follow grid planning at all. So when you look at its polar histogram, you can see its streets point in lots of different directions, not just a few. And if we look at more cities, we can start to see some patterns. So this is the polar histogram of 25 different large US cities. And these are core central cities, not suburbs. So we're looking at a single municipality's planning jurisdiction. And central cities in the US tend to be mostly laid out in the 19th century, given when the US largely developed its central cities. Not everywhere, but mostly. We can see some patterns. Most big central cities in the US follow a grid pattern. There are a few exceptions. We already talked about Detroit, which has a couple of grids in the core city. Boston, we just looked at as well. But notice Charlotte there on the top row. Charlotte is a really high entropy street network. That is, its streets point in all directions in an almost uniform distribution, a maximum entropy distribution. If we start looking at more places all around the world, we can start seeing other patterns. So I've done this analysis for thousands of cities around the world, everything from Pyongyang, Baghdad, Mogadishu to New York and Los Angeles. This is a sample of 100 of them, sorted by how ordered they are. So the most ordered on the top right to the least, or sorry, top left to the least ordered on the bottom right. That's the highest entropy on the bottom right. And you'll notice in the top row, starting with Chicago, we have lots of North American cities. In general, those North American cities follow the patterns that we were just talking about. Um, Very highly ordered, low entropy street networks because they were built on a grid mostly in the 19th century. But as we move down, we start to see that around the world, that's really kind of an outlier. North American and Latin American cities are very often planned that way. Some Japanese cities are planned that way, but in a lot of other places, we see other kinds of street network patterns, particularly in European and a lot of Asian cities. We don't see those kind of orderly, orthogonal, consistent grids everywhere. When you get down to the bottom row, you see how high entropy some places are, where their street networks really do come close to approaching that maximum entropy uniform distribution around the compass. And perhaps most interestingly, out of all these cities, Charlotte, North Carolina remains the highest entropy, much more like other parts of the world than like other US cities, just based on how its street network developed and how circuitous its streets are. So, what we can do with this now to start trying to understand street network design is looking at it in conjunction with a few other indicators that tell us about the efficiency and connectivity of a place. So here on the far left, we have what I call high griddedness, and I measure this with a grid index that combines straight streets, high orientation order that we were just looking at, and then a high proportion of four-way junctions, meaning that you have lots of connectivity through the urban tissue. Now, the other three panes here in this figure show what happens if we reduce just one of those three characteristics while keeping the others high. You either have a disconnected grid or a circuitous grid that isn't really a grid, um, or really low orientation order that isn't really a grid either. So we need all three of these things to make what we consider a grid. So if we measure this griddedness around the country, here we're looking at the contiguous US, we can really clearly see the spatial legacies of that 19th century expansion. And in particular, as you look around the country, you can see this kind of archipelago of grids in the central cities, even in places where you don't see a lot of griddedness elsewhere. And as you look at the general terrain of the country, you might start hypothesizing some other covariates here that help explain griddedness. For example, tract size is probably related. Very large tracts may be less likely to all have their streets pointing in the same direction, the more and more space that you're consuming. Topography probably plays a role. It is hard to lay out a grid in the mountains because streets have to wind to get up the grade. Of course, no one told San Francisco that, so it tends to have a grid that just cuts right up over all of its hills. And then also the era of development. That is, I've been talking a lot about this idea of 19th century urbanization when most of our center cities developed. But the US urbanized a lot in the 20th century as well. And as you look at this, you might notice that, for example, in a place like Chicago, you can see really bright yellow griddedness in the older parts of Chicago, but it's surrounded by a suburban and exurban band of lower griddedness. That is, those kind of 20th century communities that developed with more circuitous streets, lower intersection density, lower connectivity, for the sake of automobile travel. So if we unpack that idea of the era of development, we can start to see some interesting trends. So this figure shows us a snapshot of average characteristics today, in the present day, of street networks that were built in different eras. So what I did for this is I looked at each tract in the country and I tagged each tract with its decade of development, either pre-1940 or each of these decades after 1940. And I did that through a combination of tax assessor data, property transaction records, to try to understand when first structures were being built there, using the theory that street networks are typically laid out around the time that buildings are first being built in a place. So what this tells us in this figure is what things look like today based on when they were built. So street networks built in the 1940s should still look different today than those built in the 1990s because street network form is approximately permanent. It's really hard to change street networks, especially in a country with strong private property rights and somewhat democratic planning regimes nowadays. Street networks stay for a long time, as you can see when you go to a place like, even London or let alone Venice or Naples, and have street networks for centuries and centuries. So if we look at these patterns over time, we can see from pre-1940 through the end of the 20th century, this really clear trend towards sprawl post-war. That is, across all of these dimensions, there's a pretty consistent story that griddedness declined over time, orientation order declined, the straightness of streets declined, the proportion of four-way intersections declined while dead ends increased. Intersection density declined while average street segment length, so the block length, increased over time. But interestingly, if you look across these variables, there has been this reversal since the year 2000. So in the past couple of decades, we're starting to see this kind of preliminary trend toward these more contemporary planning paradigms like the new urbanism and smart growth that promote this return to more traditional urban forms, including more walkable streets. So denser street networks, more navigable street networks that are easier to provision transit lines on than through winding suburban cul-de-sacs, and higher connectivity. So you don't have to route all the way around a bunch of blocks to get to two places that are adjacent in space, but very distant in the network's topology. So there is some promising but preliminary evidence that some of those kind of popular evidence-based planning paradigms over the past 20, 25, 30 years are showing up in practice of what we're building in the past 20 years. But with one big caveat, that we build far fewer tracts today than we did in the previous decades. So maybe we're building better street networks nowadays, but we're just not building very many of them because we don't build much in America anymore. Okay, a couple more things that I want to show you before I transition to demonstrating how to do some of this street network modeling and analysis. First off is I recently expanded that US-based analysis to model and analyze the street networks of every urban area in the world. So rather than just looking at US cities, which have been studied to death by transport planners because we tend to have pretty good data and a lot of transport researchers in this country, I was curious about places that we study less. So not just looking at, North America, Western Europe, China, which have tons of empirical evidence at this point, but looking more consistently around the world. So to do that, I used urban area boundaries from the global human settlement layer, which gives us consistently defined urbanized areas around the world, and then OpenStreetMap data, which has some sampling biases that are important to keep in mind. But for cities, urban areas, and drivable infrastructure, it tends to be it's pretty good. It's the best in class at this point for doing these kind of models. So I did these models using a tool called OSMNX, which I mentioned is a Python package I developed that I'll demonstrate here in just a few minutes. For each of these models, I calculated elevations and street grades, so rise over run, to understand for non-motorized travel, how you might want to minimize elevation change if you're on foot or on a bike. And then calculated a bunch of street network indicators, so a couple dozen indicators for each of those urban areas. And then looked at street network design in different places around the world. So all the code models and these indicators here are available in open repositories where I put them all for public reuse. Really briefly, a couple of interesting things that that came out of this. One of the goals of this project was trying to shift toward urban science without samples. So rather than taking a sample, which is often a convenience sample in practice, trying to understand the characteristics for every urban area in the world, not just, say, 10 European cities or 40 Chinese cities, but trying to understand what all city street networks are like, both together and then also stratifying them for sub-analyses to understand differences between them that get masked, that with that heterogeneity being masked when we look at everything all together. So here, what I did, I just tested a couple of, so this is 4 bivariate hypotheses that have appeared in the urban science literature over the past 15 years, and just testing those relationships across all cities in the world rather than just, say, 40 cities somewhere. And a couple of interesting things came out of this. So one is the power of scaling laws that's been talked about a lot in the literature in the past 15 or so years. Um, One thing I want to highlight here is that infrastructure scales sublinearly with population, and that's important, right? So it means that people, density, make the cities more efficient. So a 1% increase in population is associated with a 0.9% increase in total street length and a 0.95% increase in intersection count. That is, more people are able to share the existing infrastructure as you densify a city. There isn't a linear relationship of having to build more infrastructure linearly for each new person who moves into the city. And then a couple of economic indicators here as well. Obviously non-causal, just looking at these elasticities or linear coefficients between them. But what I want to close on here for just a moment and then shift to demonstrating um, some of these tools for a few minutes is this kind of big picture idea that underlies and has motivated all of my work. So all of this work that I've done has really been heavily predicated on open source tools. So I tend to work in a Python ecosystem, so using tools like PySal, GeoPandas, and my own tool, OSMNX, to do a lot of this research. What I argue to people in academic settings is that we as academics are really well positioned to focus on tool building. A lot of the work that we do in empirical research, particularly for this kind of like quantitative science of cities sort of stuff, we inevitably are building some tools in most of the work that we do. You know, we write an R script to conduct some analyses, or we put together a Python library to download the data we need and create the models that we need. And so I argue that we need a more robust shared commons of software tools that are led by academics specifically so that we can infuse those tools with the appropriate domain theory, which too often they're not in reality. And we need to make sure they're well documented and reusable so that others don't have to reinvent the wheel. So that idea of the appropriate theory is important because we are uniquely situated as academic researchers to be able to straddle both worlds of theory and methods in what we do. And a lot of the time, this kind of quantitative science and GIS are really about straddling those two, trying to find appropriate models of spatial phenomena that really do embody our understanding of how the world works, so that we can create those hypothesis tests that we need for our research. The second part of this is about reusability. So often in science, we talk about reproducibility and replicability, but just as important, particularly in this domain of like shared tooling, is that we need reusability. Reusability means that our tools are well documented so that others can come in and use it without having to reinvent the wheel when we're done with it. That they're relatively easy to use. They have an API that people can make some sense of and pick it up relatively easily, or you provide usage demonstrations for it. I think the PySal community is a really great example of that in the Python world, having a lot of resources for people who are trying to adopt PySal as a spatial analysis library. And then the last part of this is that this unlocks generalizability, both in our own work, but also in the work of others, particularly downstream as people get to use our tools. But there's a lot of upstream benefits as well, where people can contribute to the tools that you use to keep improving it for your own research, which has certainly been the case for me with the OSMNX package that I use to do all of the stuff that I showed you today. And my goals for this, my generalizability goals are twofold. So the first is conducting urban science without samples. I talked about that a minute ago. But to me, what that means is rather than looking at the same North American, European, and Chinese cities that we so often study, because that's where we have the data or that's where the researchers are from, looking broadly more around the world where urbanization is happening in, say, Southeast Asia, in India, and Sub-Saharan Africa, or Latin America and the Caribbean, places that are often understudied relatively in the literature but are very much in need of empirical knowledge as they urbanize rapidly. And that goes into this final point here, localizing urban science. Um, at least for me, a lot of what I do is about practice in the end. So as an urban planner, all of my geospatial work is tied to trying to make cities better for humans to live in. And what that means is we can't really stop at just estimating a coefficient. You know, here's how cities are, and then say we're done. But what we need to do is find some kind of takeaways that people can use in practice. And what that often means is rather than conducting global urban science, it means making tools available to work in partnership with local communities, particularly in under-resourced countries and cities, lower middle income countries, where there's a huge appetite for these kind of analyses to target planning interventions, to target new street network designs or new land use policies. But they very don't, often don't have the technical capacity or the modeling tools to be able to do that just out of the box themselves. And I think that's partly where we come in with this idea of tool building, making free, open source, accessible, and reusable tools more broadly available to those kind of communities um, to help make the world a better place. So, with that in mind, I'm going to pause here. I guess we're going to hold questions until the end. Is that right, Diana? Should I walk through a tutorial?
Yeah, yeah, let's hold questions till the end because I imagine there might be a couple about the demo itself.
Okay. Yeah, so let's do that then. And what we can do is
I mean,
just
if that makes sense to you, Geoff, unless, does anyone in
totally.
the audience have a important question right now that we want to turn to before we watch Geoff demo some of the tools he's created?
Okay, so what I
Yeah,
can do then, if not, is I can just jump to sharing my
yeah,
browser instead of Zoom here.
sure.
And you can feel free to follow along too if you'd like. Let me see, where's my, share my desktop. Okay. Can you see my browser now?
Yes.
Okay, great. So I'm on this GitHub page. This is probably the easiest way to find it if anyone wants to follow along. It's github.com. My username is gboeing, and these are the OSMNX examples. If you just go to my GitHub page, gboeing, it's here pinned. If you wanted to come here and follow along on your own computer or to do it later, it's easy to find. And there's a button here. If you just scroll down, it says open in Colab. So that's all that I'm going to do today. And you can do the same if you want to run this without having to install anything. So I'm going to open Colab and I'm going to do just this first notebook that pops up. It's numbered 00. I do zero indexing because I work in the Python world, I guess. This is the OSMNX features demo. And this notebook just walks through some of the features of the OSMNX Python package that I mentioned that I used for a lot of that research that I showed you today. It's a Python package that I developed and maintain. And what it does is it lets us work with OpenStreetMap's APIs to automatically build models of street networks or any other spatial network anywhere in the world with one line of code. And then you can, once you've modeled it, you can analyze it and visualize it using pretty powerful Python tools. The models that it makes are Network X, multi-digraphs. Network X is the standard network modeling and analysis package in Python, so you can automatically work with that. You can turn them into spatial data frames with GeoPandas if you prefer to work with your spatial data that way. You can dump it all to a geo package if you really just want to work with it in a desktop GUI-based GIS. Save it as a graph file instead if you want to work with it in other graph libraries. So it's kind of like glue code. OSMNX lets you get a model and conduct analyses with it. And this notebook shows some of that. So I'm going to let Colab install for me. You just got to uncomment this line to do a UV install here for OSMNX and its dependencies. It takes just a minute to do that. And what I'm going to show you today is some of the basics of working with OSMNX. In particular, how to download and model street networks, and then a few of the analyses that we can do. So I'll just take 10, 15 minutes more to walk through some of this. This is the first of something like 20 notebooks that you're able to walk through as examples if you're interested in continuing with this. So to walk through this from the top, I'm letting this run ahead because it takes just a second. Colab's kind of slow and it's got to do some data caching. So from the top, I installed OSMNX and its dependencies. I imported NetworkX and OSMNX. So NetworkX is a generic network science package for Python. OSMNX is our link between it and OpenStreetMap. In this first cell of stuff, I told OSMNX to get a graph from place. So graph here just means, say, a model of a street network or a model of a network. And I can provide a place name. In this case, this is Piedmont, California, a small town in the Bay Area, which OSMNX will automatically geocode to Piedmont's boundaries, and then download all of the drivable street network inside those boundaries. So you can specify these these built-in network types, like drive, walk, bike, and so forth. Or you can specify your own custom filter to get exactly the kinds of streets that you would want based on OpenStreetMap's really rich tagging scheme. So in one line, we built that model, and then in the second line here, I told it to plot that graph. And it gives us this. So we have Piedmont's street network here. The gray lines are network edges, streets, and the white circles are intersections and dead ends. Those are the nodes, the edges and nodes of the network. Um, so the goal of the OSMNX project is just to make this really easy. You have to know enough Python to write one line of code, and you'll have a model of a street network. Trying to make it as intuitive as possible so that as many people can do this as possible. And we talked about that idea of infusing our tools with theory. One of the problems that I had when I started developing this package is that we didn't have street network models that really did a lot of the stuff that we needed of them to be a good network model. That is non-planar, so it had to allow bridges and overpasses rather than nodes at every line crossing. We needed to be a multi-graph, meaning you can have multiple streets connecting two intersections, which often happens in the suburbs. A directed graph so that we can model traffic flows properly on it, being able to easily incorporate elevation data so we can understand the topography under the network, to understand how arduous different paths are for non-motorized travel. So I talked a little bit about this, so what it does, and how it works. There are a lot of different ways that we can create these models anywhere in the world. We can make fully bidirectional networks, so that the driving network has streets in every direction. That is, maybe I want to know how people walk on the drivable network rather than just flow restrictions. We can also create undirected graphs, similar kind of thing. And we can create a directed graph without parallel edges. And the reason for all of this nuance is because there are different graph algorithms that require specific graph data types to run. And having all of these conversions happen in ways that properly select stuff in the network in the conversion, make it so you have the best possible model to run those algorithms on downstream. We can convert our graph to different data types. So I mentioned that we can get GeoPandas nodes and edges. So if I convert my graph of Piedmont to node and edge geodata frames, and then look at the first 5 rows, the head of my nodes geodata frame, we can see this table is what we get. So there are OSM IDs to index each of those nodes, um, X and Y coordinates. Street count is akin to the node degree in the undirected graph. It's how many physical streets connect to that node. 3 means that this is a T intersection, a three-way intersection. And then some tags from OpenStreetMap. So the highway tag will tell us that it's a stop sign if there is one at that intersection. And then we have these GeoPandas geometries here as well. Same thing for the edges. You can see these are indexed by origin node, destination node for the edge. And then a key if it's a parallel edge, just to differentiate. OSM IDs, and then all the different tags coming from OpenStreetMap. We can also convert back. So if you have, say, loaded shape files or geopackage layers, as long as you put them into this format of indexing and having a few of these things that OSMNX needs, like OSM IDs or geometries, you can take arbitrary geopackages and shape files and turn them into a graph to work with using this library. Okay, so what can you do with it? So we made some models, but really what we want to do with those models is analyze them or solve routes on them or do something with them. So I'll show a couple examples of that with our remaining minutes here. First off, some basic street network stats. Um, a lot of indicators of street networks normalize by area. For example, something like intersection density tells us about the grain of the street network. And to calculate intersection density, we need to know the denominator, the area that that street network is covering. So OSMNX can handle all of that pretty gracefully here by projecting the graph into a projected coordinate reference system. Notice I'm not specifying a coordinate reference system. If I don't specify anything like here, it will automatically calculate the correct UTM zone based on where in the world my street network is and project automatically to that UTM zone. So I get a meter-based projection. So it automatically projects my graph to the UTM zone that covers Northern California. I can convert my graph to geodata frames to get this projected nodes geodata frame. And then I'll take a convex hull around it and calculate the area in square meters. So that gives me the graph coverage area in square meters without having to do anything with other packages or loading it into a desktop GIS. It does it all automatically for me in just a couple lines of code. Now that I know that area, I can plug that into OSMNX's basic stats function, which just gives us a set of basic indicators of the street network. I pass in my projected network and the area that we just calculated in the previous cell. We're going to use that as a denominator for density measures. And then one last thing I'm going to do here is I'm going to clean my intersections up a little bit. And the reason for that, if we look above, is that OpenStreetMap often has complex intersections. Here's a good example of one. We have some streets meeting here, but the way that the lines are digitized in so much detail results in there being maybe like 4 nodes for what to a pedestrian or motorist would just look like one complex intersection when you're actually on the street. If I'm calculating intersection density, I don't want this to show up as 4 intersections when in reality it serves the purpose of a single intersection. By passing in this clean intersection tolerance argument here, but I need to run that first. I'm going to find all of the nodes that are within 15 meters of each other and merge them into one. I'm going to clean up those complex intersections into one intersection object mapped to a single node. So we run this and it spits out some of these basic stats. So the meanings of each of these keys is all in the documentation, but we have here the number of nodes, number of edges, the average directed node degree, total edge length, so on, so on. Streets per node. So streets would just mean physical streets, like undirected edges. Streets per node proportions here tells us that we have, so 1 would be how many dead ends. It's about 10% dead ends. 3 would be those T intersections. It's about 77% T intersections and about 13% four-way intersections. Then we have some of our density measures like node density, intersection density. So nodes would include intersections and dead ends. Intersection density is just intersections. The clean intersection density, once we've merged those complex clusters of nodes together into one true intersection, and so on. Lots of stuff here. Let me see. Okay, I'm going to wrap this up then. I'll show you just 2 more things and then we'll call it. First off, we can save this graph to disk in a variety of different formats. So for example, as a geo package to work with in GIS, or a GraphML file to work with in other graph analysis libraries. If you want to move out of the Python ecosystem into some other ecosystem later. And I'll show you one example here of visualizing stuff. So in this example, what I want to visualize is the streets themselves in terms of their relative closeness centrality. So there are various measures of centrality in network science. Closeness centrality measures how close you are relative to everything else in the network. So more central places will be closer to everything else, like a spatial optimization thing. So what I'm going to do for this is I'm going to calculate closeness centrality using network X. The nice thing about OSMNX is the NX part. We can pass its graphs directly into network X to have access to literally hundreds and hundreds of different graph algorithms and analyses. But what I'm doing here is I'm going to calculate the line graph first. Line graph or the dual means that I'm inverting my nodes and edges. So nodes become edges, edges become nodes. It's kind of a tricky concept, but what it means is that when I calculate closeness centrality, I'm going to be calculating it for my edges instead of for my nodes here. And then I'm going to set that edge centrality as an attribute on each of my edges. So each of them are going to get the value of their centrality as an attribute. Once that's done, I'm going to tell OSMNX to get edge colors from some attribute, in this case, that edge centrality attribute, drawing from the Inferno color map. And then I'm going to plot my graph again, just like we did earlier in like the second cell of this notebook. Only this time I'm going to specify the edge color should be those edges that those colors that I just sampled from that color map. Line width is 2, and node size is 0. So we're going to have invisible nodes here. And we get this. Um, so relatively simply, I was able to calculate the centrality of all of these streets. You can see the most central part of the network shows up bright yellow. The least central parts on the periphery show up in dark purple. Nothing too revelatory about this simple example. It's about what you would expect. Visually, the most central parts of the network have the highest edge centrality values as well. In the rest of the notebook, we cover routing, so how to route between two lat long points along the network and calculate route characteristics. We also have a variety of other ways to get networks. So I showed you for the city of Piedmont, California, but you can similarly build out really explicit queries in case you're getting the wrong place from the geocoder. You can also query anywhere in the world. You can query for some area around coordinates or an address. And then you can also get other kinds of networked infrastructure. So we're not limited to street networks. You can get, for example, the New York subway network by passing in a custom filter here to get everything where railway matches subway on OpenStreetMap. And then the last part of this notebook is that we're not limited to networks at all. OSMNX also has a features module to download any geospatial features from OpenStreetMap. So you can get stuff like local amenities, points of interest, building footprints, parks, bus stops, transit stations, grocery stores, anything on OpenStreetMap, and turn it into a GeoPandas geodata frame and then plot it. So I'm going to leave it there. If you're interested in this, again, you can just go to my GitHub page under OSMNX examples. You can click the Open and Collab button if you wanted to run through any of those tutorials yourself. So thank you very much for your time in the middle of your summer vacation. I'm happy to answer any questions for our remaining time.
Thanks, Geoff, very much. I'm excited to know more about this, and I'm really glad we were able to offer this as a topic by iGuide. Any questions from the group? Oh, we have Geoff's undivided attention. I see Joe Holler typed something, and I'm gonna call on Joe. Yeah, we've got. You can probably see the uh, chat right there too,
Oh yeah,
Geoff.
let me pull it
So
up.
yeah, Joe Holler. I'll read it out loud. Um, Joe has a lot of expertise in the areas of reproducibility and reusability. He worries about the transferring methods to new contexts in which the data no longer supports the methods as well, like in
Mhm.
African cities with more errors and bias in OSM data inherently. Any thoughts on how to guide users to check accuracy, bias, and uncertainty?
Yeah, absolutely. So this has been a big project I've been working on lately. There are a couple of problems. So you mentioned African cities, which is a good point, particularly in sub-Saharan Africa. Large cities tend to be fairly well digitized for drivable infrastructure. Mid-sized cities, towns are not digitized very well. We can do some of this automatically using up-to-date satellite imagery nowadays. But what we've been doing, my main project working on this kind of stuff, is through the Global Observatory of Healthy and Sustainable Cities, where I'm on the executive committee. And what we do is we work with a partner network of around 200 cities around the world now. Those partners in those cities may be academics or someone who works in a mayor's office. But we work hands-on with them to do a lot of our validation work. So as an example, one of our cities is a mid-sized town called Maiduguri in Nigeria. And we work with them as one of our test partners when we're testing out new features. So we use OpenStreetMap data as a base layer. They will then go in because they don't have local GIS data to do a lot of this work. So what they will do is they'll go in and they'll validate it and they'll look for the street network, both coverage, so given their local knowledge of the street, looking at satellite imagery, does the OpenStreetMap data cover what they expect, or where specifically are we missing links? And then secondly, for connectivity. Sometimes places in sub-Saharan Africa, in India, in Indonesia, when they're digitized, they'll be automatically digitized in ways that don't have perfect topology. So streets just almost connect, but they might be a millimeter apart. And that means that we have this broken connection that doesn't actually look like an intersection in reality. So they help us with that so that before we're going through and doing any analyses on this, we have our local partners with that local knowledge verifying that the model represents what it should model according to them. And we do the same thing for amenities, land use information, because we model access to things like schools, fresh food markets. In fact, fresh food markets is an interesting one that has a drastically different interpretation in a place like Chicago than it does in Mexico City or in Mumbai. So we have to be really sensitive to those local contexts. It's a very long, rambling answer, but what I recommend to your specific question about how to check that kind of accuracy, bias, uncertainty, what we have found we basically have to do if we're not based in that city is we can't make any assumptions about it. We need to work with local partners with local knowledge. There really is no other way other than that kind of field work and local expertise for us to be doing those kind of analyses.
That's thanks for that response, Geoff. Joe Holler, if you've got a follow-up question, let me know. I put the link to that Global Observatory of Healthy and Sustainable Cities in the chat. It's an entity I'm unfamiliar with, and I'm glad to know about it. Any other questions from anyone in the group? Xiaowen Wang, is there a question? Oh, we've got a raised hand from Stephen Baker.
Trying to do this.
Sorry, Xiaowen, I just jumped right over you. I'm going to go to Steve.
Xiaowen, you want to go ahead?
Go ahead, Steve.
Okay. So I appreciate several things about the presentation today. One of them is, calling out academic contribution and theory. And my question is where you think we are, and you kind of answered this actually at the end of your last, the answer to the last question, which is where we are in having a good local theory that allows for the application of a universal tool. And I say this as someone who's been at the University of Chicago for a long time and is familiar with like the Chicago School of Sociology and how cities develop and all of that stuff. And now we're in the global South and we're in the West and a whole bunch of things. So there's a whole bunch of local theory that I see needing to be developed and getting developed.
Yeah.
And so I'm just curious where you feel like we are in our local theory robustness, perhaps.
Yeah, of course. I mean, well, yeah, I guess that's really the argument from a lot of the seeing from the South theorists, right? That what we call theory in academia is very often white, male, Western world centric theories of cities based on the cities that we have as our convenient samples. If you live in Chicago, you'll take Chicago as your model of urbanization. Similarly, what 25, 30 years ago, we had the Los Angeles School of UCLA and USC-based scholars saying that Los Angeles is the archetype of modern urbanization. Ironically, they were all people who lived in LA, right? Like, no wonder. What we don't have, though, is that strong of theorization coming out of the global south, often because we don't have the empirical work there, often because academic institutions with the most resources are based in the global north. But what I hope is that maybe that twofold approach. Sometimes generalizability, doing urban science without samples, is a useful way to understand what cities are across all cities, but very often the real action is in localizing urban science. What I mean by that is I think that general theories aren't that useful for solving most real world problems. It is those, getting an elasticity for how the average city around the world has this relationship doesn't really help me if I'm an urban planner trying to make Abu Dhabi more walkable, or trying to make Jakarta more walkable, or trying to make Johannesburg more walkable, right? It's about local culture, local economic conditions, local perceptions of safety, crime, local willingness to shift out of cars, the climate, the street network design, the design of the buildings facing the street and street trees to give shade. There's all this other stuff that makes those kind of global coefficients and global theory less useful a lot of the time for a practicing planner. And so I guess what I hope is when we're talking about theory-infused tools, we're talking about the appropriate theory, whatever that means in the context. And for the Global Observatory project, a lot of it has been shifting as every year goes by, as we learn more from our partnership network, all the things we took for granted, like what access to fresh food means in Sydney and Los Angeles versus in a small town in Mexico or in Nigeria, and trying to make our tools more flexible so that local context can be reflected in them through configuration, through that local knowledge.
Steven, you're muted.
You're calling for both a kind of inductive development of theory as well as application of the theory you have with some, awareness.
Yeah. I mean, I think as tool builders, as academic tool builders, the tool isn't the end in and of itself, right? We're still trying to contribute to these broader aims of science and theory, making the world a better place. Yeah.
Okay. Xiaowen.
Yeah, thank you very much, Geoff, for presenting your very interesting work. And we already have, well, by the way, I'm Xiaowen Wang. I serve as director of the iGuide Center. We already have researchers in the iGuide Center community using your tool. Let me pull this in the chat. So for instance, if I search OSM Next on the iGuide platform, which is our community platform for sharing computational notebooks, as you just did, publications, data sets, and other knowledge elements in an interconnected way. So I think what you presented, I have a couple of points. One is your vision for meta-analysis is really powerful. So, the tool and the theory you baked in your tool allow the research community to do comparative analysis across different locations. I thought that was really exciting. And what I want to highlight is this community platform iGuide has created is essentially striving to support the community to share such comparative knowledge, meta-analysis approach in an interconnected way, meaning connecting data, notebook, code, publication, even educational resources together. So I would encourage you to explore this platform because I see a growing community in the iGuide space and broader than iGuide could benefit from your knowledge and the further development of your tool, maybe even contributing to your tool development. And how do we foster this potential synergy, I think is intriguing to me. Another point I was thinking to make is in the work some iGuide colleagues have done in the kind of network data analysis in urban contexts, I learned was sometimes running to bottlenecks, especially computational bottlenecks for large networks, because this is inevitable when you do meta-analysis. So I wanted to learn from your insights, your vision going forward, how to scale this up.
Yeah.
When you do large scale, multi-scale analysis of such urban networks, what was your experience dealing with the, computational bottlenecks, and how to make this more scalable for the broader community's benefit? Thank you.
Yeah, that's a great question. A couple of thoughts on that. First off, as you noted, a lot of this can be really memory inefficient to build graph models. In particular, it's one of Network X's biggest weaknesses. Network X is fairly memory inefficient compared to a lot of network analysis tools. If that becomes a bottleneck, which it often is, what I do is I will convert my graph to iGraph, which is a different network analysis library built in C and a lot more efficient. Or you can convert your graph to RustWorks, which is a reimplementation of Network X in Rust, faster and more memory efficient. That doesn't do it. The other thing that I do, a lot of my work for my lab, what I have my grad students doing is working in a computing cluster that we have on campus. So they will provision server space, and then we'll often parallelize things to make it go faster. A lot of these kinds of algorithms are CPU bound in most of these libraries if you can't move it to a GPU. So if you just end up spinning up 100 CPUs in the cloud, have them doing one city apiece, it can take maybe a couple of hours, sometimes on a big city, to solve all of the centrality indicators. But parallelizing it, provisioning cloud RAM rather than local RAM on your own desktop or laptop, and then shifting from Network X to compiled C libraries when needed can make everything faster and more efficient. There's no silver bullet though. The problem with a lot of graph algorithms is that they scale with node size. So if you want to analyze the New York metropolitan area, you're stuck with several million nodes. You can make it more memory efficient by running that intersection consolidation algorithm I talked about earlier. One of the benefits with OSMNX is you can get a much more parsimonious model than you otherwise would from OpenStreetMap data. But at some point, you're facing the physical limitations of algorithms and hardware, and then it's just distributing it and provisioning RAM.
Along those lines, because the iGuide platform does have access to a fabric of high-performance computers across the country, particularly those supported by the National Science Foundation, if we could potentially partner with you, have the methods you mentioned integrated and also shared with the broader community, and also empowered by the backend resources from the platform. And then allows for this reusability to occur, as you highlighted. I think that could be even a boost to making the OMNX and related spatial analysis methods more broadly available to the community.
Yeah.
Thank you. Thank you again.
I'm
Thank you.
sensitive to the time. I know we've crossed over the top of the hour. There's one quick question here, just maybe it's a quick answer that Joe Holler has as a follow-up. Wondering if your approach to parallelization is always dividing the problem geographically so that each processor works on a different geographic extent.
No, it doesn't have to be. So OSMNX has built in some multiprocessing directly to it. So on a single graph, you can solve some problems in parallel on a single machine. You can't distribute that task across multiple machines. But if you're doing comparative analysis, usually the easiest way, say if I have 10,000 graphs I'm going to analyze, the easiest way is just dividing up 100 to each of 100 CPUs. But it doesn't have to be that way.
Okay. I'm gonna just ask for Geoff, if you've got one more minute. If I know this can be high level comments, but someone had asked before about how do you see the role of AI in deep learning and urban network analyses? Maybe if you can just have just some final comments on that for a minute before we
Yeah,
sign off.
the topic du jour, right?
Yeah, it's true. Thanks for entertaining this just really briefly.
Yeah, no, of course. It's an important question. So I'd say two things. The first is that graph neural networks have become really useful in the past few years, I mean, pretty recently, for being able to analyze phenomena on networks. Much more powerful than a lot of the other tools that we used to use were. The second short answer would be for validation. To Joe's question earlier about how do you know if it's accurate? We can increasingly use computer vision to help us with that question by taking our model of the network and satellite imagery or other remote sensing imagery, even street view imagery now, and being able to check to see if the patterns appear in the imagery that we expect given the network. And it can also help us highlight on the network model where we think there are modeling problems, data problems, that we can go back and check specifically. It takes a huge amount of labor off manually checking everything. Though that's what hiring undergraduates is for, right?
Yeah, no, thanks for that. I think that type of use of AI is something that iGuide's been working on too, and we'll see some examples of that coming up with our summer school next week in Boulder. All right, again, thanks everyone for coming today. This session has been recorded, and once it's processed, it'll be up on our website with all of our other VCOs. Thanks very much, Geoff, for your time and sharing your expertise with us today.
Yeah, thanks everyone.
All right, thanks. Bye-bye.